Hello, Math 30-1. Our travels with functions continues, and this is probably the deepest and most applicable type of operation with functions, where we combine two functions. There are many situations where one function gets nested inside another, or where we have an outer function, inner function, composite function. So in this first example, please read through it. And as you'll do, you'll notice that, well, we can express area in terms of the radius, and clearly area is equal to, in terms of the radius, is equal to pi r squared. But they also, in terms of this, are talking about the radius is really 0.3 t in terms of time. So where is the radius in terms of time? Well, the radius is moving at 0.3 meters per second. So if we wanted to know the area of the circle with respect to time, we simply nest the radius inside of this, and so really area now swallows up the radius with respect to time function, and wherever you used to see r, you now replace it with r at t, and therefore we have pi times 0.3 t squared, which now makes that new formula equal to pi times 0.09 t squared. And so now that will give you the area of the circle at any given moment in time, not just at every given radius. So that's an example of a composite function. In the next example, they're talking about the liters that a car uses. So it says that in this case, this car is using 8.2 liters for every 100 kilometers. So therefore, if I use 8 liters for every 100 kilometers, then distance divided by 100 times 8.2, or in other words, the amount of liters of fuel I use for every kilometer is 0.082 per kilometer. What's the cost? Well, the cost is simply 1.25 times every liter you use. So in this third example, anybody who's driving a car, really what they really care about is how much is it going to cost me to drive that far. So what we're really interested is what does it really cost me to drive a certain distance. And so I know what it costs me per liter. I know how many liters my car uses. So if I can combine these two and have liters, as you can see, have liters in this equation be replaced with D, well, all I really need to convert is liters can really be expressed. Liters is equivalent to 0.082 D, so really I can take that 1.25 L and rewrite it as 1.25 times liters are really 0.082 D, and so by having one function be nested in the other function, we end up with a new equation which gives us the cost per liter that we travel, and that is 0.0125 D. So that's an example, a real-world example of composite functions. And now I want you to go and investigate, as we usually do, and play with this. And this may make perfect sense and it may not, but I want you to go through the investigation on page 33 and 33 and come back and look at this when you need to. So if you've read through, that may or may not make sense, but as we go through, I think it'll become clearer. So composite functions, as you can see, I have h at x, which is the composition of two other functions, this one and this one. And if you look at it, it says it's composed of g at f at x. It's read as g of f at x. And you can also write it as h at x is equal to g OX, or just a different notation. Those are equal in terms of what they are stating. When h at x is written as g at f at x, note that f is applied to the first function and g is applied to the second. And h is often referred to as a function of a function. So it's a composite function. And we're going to look at examples 1 to 4, and this idea is really important in the chain rule and so on when we do it in calculus. You have to be able to see, and mostly you just need to see what's the outer nature of this, and what's the first thing that happened to, what's the big thing that happened, and what's the secondary thing that happened. What's the nested function? How did it work? So in this case, describing words, the two operations. Well, it looks to me like what happened to the original x. Well, it looks to me like x got squared, and then we subtract 2. And so when you look at this, x got squared by f. That's what f did to it. That's a function. That's an operation that's happening. So that became x squared. And then you subtracted 2. That's what g did. So then you end up with a final situation of x squared minus 2. So what was f at x? What was its nature? It took whatever it got and then it squared it. That's what f did. It said, hey, give me an input and square it. What did g do? G was the subtract 2. So it takes whatever it gets, and then it subtracts 2, no matter what goes in there. G is x squared minus 2. So if g ended up with a happy face inside of it, that's what was the input, then it would be happy face minus 2. Whatever its input is, it subtracts 2 from whatever you throw in there. We threw in an x squared, it came out as x squared minus 2. So what is the actual thing that g at x does? It is really x minus 2. That's what it does. All right. Consider the composite function this. Well, you can see what's inside. This is the inner function right here. That's what happens to it first. And then this is the outer function. So inner and outer, describing words, what happens? Well, it looks to me what we did to x is we took x and we then added 4. That's what we have to do first, kind of like order of operation. And then what do? We cubed it, right? We cubed it. That's not very neat. We cubed it. We complete the diagram and say, well, what happened? Well, in this case, again, I think I'm supposed to add 4. And if I do that, I end up with x plus 4. And then what do? Well, it tells me that I'm supposed to cube. And when I do that, I end up with x plus 4 cubed. So what are these functions that are building h? There's two things, right? F at x is the adding 4 machine. Takes whatever it gets and it adds 4. Now the input that g got handed off an x plus 4, and what does g what does that function do? It then cubes it. So that's x plus 4 cubed. And so what's the actual function that g at x does? It takes whatever it gets and it cubes it. All right, takes whatever it gets and cubes it. So it says developing method. Consider two functions. So those of you that are really, really comfortable with functional notation and substitution, this will really go. And for some of us, we may not see it right away, but it will come. Just take some practice. The function f is multiplying by 3, so that is obviously going to take that input and that will turn into 3x. The function g says we'll subtract by 5, so that becomes 3x minus 5. H at x is equal to g at f at x. And what is f at x? F at x is 3x. So when we substitute that in there, that's what we have. And what does that actually turn out to be? 3x minus 5. Now, if you look at k at x is where we have g at x that got swallowed up by f at x. So in this case, one way to look at it is, well, just do substitution. I have a function f. I know what it is. Function f is right here. It's a multiplier of 3. So what is inside of f right now? Inside its belly. Its input is g at x, which is x minus 5. Just substitute it in there. G at x is x minus 5. What are you supposed to do to x minus 5? F says that I take whatever is given to me and I multiply by 3. So that would be 3x minus 5, because that's what f does. It takes x minus 5 and puts it in where you see x. So we end up with 3x minus 5, and that gives us 3x minus 15. And you can go to and do assignments 1 to 6 if you want, or you can continue on. So what are the steps? It's going to be the same anytime we have a composite function. So if we look at, in particular, this example, and we complete the work and go step by step through, don't want it to make it really complicated, but again, the steps are the same. What is f of x? Go back up here and just look. F of x is right there. That's what's inside of G's belly. Inside of G's belly is 10x plus 1. And I'm hoping that you have this concept that a description of a function means that you take whatever input is. So if I told you that G, I wanted you to input a happy face into the function G, you would simply say, oh, Mr. K, that's easy. That's just 2 happy face minus 5, because G takes whatever you input and you multiply by 2 and subtract 5. So here we're being told to put in 10x plus 1 into G, and that means that the formula is going to be 2 times 10x plus 1 minus, 5. And when we simplify that, clearly that's 20x plus 2 minus 5, which then results in 20x minus 3. And once you sort of see that pattern, it really becomes pretty straightforward. What is G of f of x, right? Well, it's better if you write it in this form first. That's really G with f of x inside of it. And so what does that mean I'm supposed to do? Well, that's really G with an input of f of x, which in this case is 2x squared minus 1. And what does that look like? Well, that is 3 times 2x squared minus 1 minus 4, which simplifies to be 6x squared minus 7. Now, sometimes you can have a function nest itself into itself. So GOG at x, or GOG, is really G with G at x inside of it. And therefore, well, that's G with an input of 3x minus 4. And that's put into the function 3x minus 4. So that would be 3. There's my input minus 4. And what is my input? 3x minus 4. And so that becomes 9x minus 12 minus 4. And I end up with 9x minus 16. Now here's where it's really important. Domain and range, and we've seen that in rational functions and so on, that when we do transformations to functions, that domain and restrictions and things are very, very important for us to be aware of. All right? So I want you to follow through. By now we probably have this. I want you to follow through and complete this investigation. We'll come back and chat. All right, so FOG at 2, that is F at G at 2. And we might run out of time on this screencast. We might have to have a part 2 to it. But F at G at 2, when I plug in 2, and I'm going to do this in my head, when I plug in 2, I'm just going to do this on the side. When I plug in 2, I end up with, when I plug in 2 into G, as it says here, I end up with the square root of 2 minus 1, which equals 1. So what is G at 2? It is 1. That's why I'm just going to put F at G at 2 is now F at 1, and F at 1, when I plug in 1 into F, I end up with 1 squared minus 3, which is minus 2. So F at G at 2 is negative 2. What is FOG at 0? Well, that is F G at 0. What is G at 0? I go up and I look at G, and G at 0 is undefined, and therefore this is undefined. So we can't find an answer to that. I look at G at F at 2. What does F give me if I stuff in 2? I get 4 minus 3. F at 2 is 4 minus 3, which is 1. G at 1 gives me 0. So G at 1 is 0. And lastly in this chart, the one we'll have time for, GOF at 0, that is G at F at 0. What is F at 0? When I plug in 0 into F, I end up with negative 3. So this is G at negative 3. Can I plug in negative 3 into G? No, I cannot. That is undefined, right? If you plug in G at negative 3, you end up with the square root of negative 4, and that's not cool. You need to go to part 2 of this screencast to hear the rest of the story.